Hello, this lecture is intended to show you how you can make your teaching more brain-friendly. To do this, first of all, I'm going to describe what is cognitive load, which may be a term you're not familiar with, show you how PowerPoint can unfortunately increase the cognitive load on your learners, and then how we can still reduce this cognitive load and be able to teach effectively. I want to show you how slides like this, which is a pretty common sort of slide that we might see, or slides like this, which unfortunately we also get to see quite a lot of, or even a slide like this can sometimes just have the effect of doing this to your audience, which I think we'll all agree is not really the desired outcome. John Sweller, who is a cognitive neuroscientist from Australia who's studied this extensively, has said the use of PowerPoint presentation has been a disaster and it should be ditched. Well, that's a little bit of a sweeping statement. However, what I would counter it with is that PowerPoint doesn't kill presentations, it's the way that people use it that does. Bill Gates has given us a great tool. He's given us a tool that we can do a lot of different things with, as well as lecturing, and we can do it in a lot of different ways. Unfortunately, he's also given us a tool that will allow us to make slides like this. You could pretty much spend an entire hour lecture trying to explain this slide to the audience, and at the end of it, they still wouldn't have a clue what you're talking about. And one of the problems is the different ways that PowerPoint gets used. It gets used for prompting the speaker, and particularly for speakers who are less experienced and they feel that they need to have every word there in front of them. They put a lot of words on the slide and then they're reading those slides. There are other ways around this. It gets used for presenting all of the data. So every piece of information that you've acquired on a study gets presented to the audience as part of a 7-minute presentation at a national conference. All of the data should go into the paper. It doesn't necessarily need to go into a 7-minute presentation. We all try and teach too much. So we try and teach our learners, be they students or residents or CME level learners, everything that we know about a subject instead of trying to teach them the most important things they really need to remember. We try and use the same set of handout as a handout for our learners. So we want them to take home those slides. We don't want to have to write a separate lot of lecture notes for them. So those PowerPoint slides get given to them in either a hard copy or PDF copy as their resource to be able to look back on. But are we really using PowerPoint to teach in these circumstances? Can we teach effectively while we're using PowerPoint as our notes for the lecture, as a means of presenting all of the data, and as a handout for the students? And here's the key point. It's not what you teach during any lecture, it's what your audience learns that is really important. So let's think what we want our learners to do when we're giving a talk. We want them to pay attention. We want them to understand what we're saying. We want them to remember what we're saying. And we want them to be able to take the information that we've given them, the tools that we've given them, and be able to think out of the box. We want them to be able to apply what they've learned to different situations. If I show a resident what left upper lobe collapse looks like on a chest x-ray, it's going to be no help to their future patients if all they can identify is that particular left lower lobe collapse pattern in that particular size patient, in that sex patient, in this degree of severity. They need to be able to acquire those skills and be able to apply them to a whole variety of different left upper lobe collapses, in a whole variety of different body habituses, in both male and female, and young patients and older patients, and so on. And this is called far transfer of learning, as opposed to near transfer of learning when you're only able to apply it to identical situations. You may have seen something similar to this before, the learning pyramid. This shows how much learners retain when the information is given in different forms, such as teaching others, discussing the information, or unfortunately, in our most common means of teaching, which is lecture format. So learners retain probably less than 10% of the information given in this kind of a format. And considering the vast number of hours it takes to be able to get a new lecture together, let alone the time wasted by learners listening to that information, This seems a colossal waste of time. So we really need to try and maximize what they get out of every single lecture we give. This graph is one way that cognitive neuroscientists measure how efficient learning can be. I'm just going to explain it to you because I'm going to be coming back to show you a couple of examples of these later on in my talk. So on the y-axis here, they map how well a learner performs after having any type of a teaching session. Performance might be how well they remembered the material or how they could apply the skills or the material that they've learned. On the x-axis is mapped the mental effort that it takes for the learner to be able to acquire that information or learn that particular skill, and this is usually measured by some form of a standardized subjective scale applied to the learners afterwards. Now we want learning to be up here. We want the learners to perform very well after our session, and it would require very little effort for them to be able to learn the material. What you don't want is learning to be down here, that the poor student or resident is working incredibly hard to be able to learn this information. At the end of it, they still remember very little. So coming back to this term cognitive load. So the cognitive load is the mental load which is imposed upon our brains by us trying to learn new processes or learn new data. And the reason there is such a thing as cognitive load is because of the limitations of our working memory. We have two types of memory. You may be more familiar with the older terms, which were short-term memory and long-term memory, but they're now called working memory and long-term memory. And I'd like to make a couple of computer analogies here. Our working memory is like the RAM in our computer. It has a very small capacity. It doesn't hold information for very long, and then the information has to be either transferred into long-term memory, in this case the hard disk, or if you turn your computer off, it's going to disappear completely. Working memory and your RAM processor is, however, crucial for being able to process that information, to be able to get it into a form where it can be stored in long-term memory. Your long-term memory is more like the hard disk in your computer. It has a supposedly infinite capacity, it holds information for much longer, it stores much more complicated memory patterns than are able to be held within working memory, but it is very dependent on the working memory for getting the information processed and into the long-term memory storage. It turns out that the capacity of your working memory really is very small. In fact, you're only able to hold 7 pieces of information, plus or minus 2 at any one time, and this is some studies going back to the 1950s. This probably explains why many of us have problems looking at a 10-digit phone number and then dialing it straight out without looking back at the original number. After we exceed this very small capacity of the working memory, information has to be either stored within long-term memory or it's going to be lost to us. When cognitive load gets too high and it exceeds the capacity of the learner's working memory to be able to process and store that information, you risk losing more than just those last little additional pieces of information. It's kind of like when you blow a balloon up and it bursts, you don't just lose that last puff, you lose all of the air within it. So when we make the cognitive load too high for our learners, it may result in them actually learning very, very little from this particular session. Cognitive load is affected by what we're teaching. Obviously, it's much easier for people to learn, say, simple arithmetic than it is for them to be able to learn calculus, so I'm not going to talk a whole lot more about that. It's affected by how much we try to deliver to them in any one teaching session, how we deliver that material, and in particular who we are delivering that material to. It turns out that we can very easily increase cognitive load through some very simple things when we do our presentations that we may not be aware of. When we increase cognitive load, our brains do unnecessary cognitive processing, and this decreases the learning. Going back to the computer analogy again, think about when you're typing on your computer, you're in Microsoft Word, and it's going slower and slower and slower. The letters are just kind of popping out one by one. You look down and you don't know what's going on, it's the only program you've got going, and then you look at the toolbar, open up Task Manager, and you find there's 137 different processes going on that you were unaware of. That slows your RAM processor, it slows things saving into memory. And a similar process happens in the brain when there's unnecessary cognitive processing going on. Read the words on this slide out loud to yourself. Now read the words out loud on this slide to yourself. Which one was easiest to do? For most people, this second slide is much easier to read because the colours are concordant with the words that are written there. With the first slide, you're looking at it and you're saying, wow, the word says green, but it's coloured red. The word says red, but it's coloured purple, and there's a little dichotomy going on in your brain, a little conflict going on. It's increased the cognitive load, and a very, very simple exercise becomes a little bit harder. Let's look at another example. What is this a picture of? I'll give you a couple of seconds to look at it. Well, if you didn't get at it, look perhaps at this. What's this a picture of? I think most of you, at least from the northeast, recognize that this is the coast of Boston, and there's Cape Cod at the bottom corner, which gives you the clue. So why was this one a greater challenge? Well, because I've inverted the colours of land and sea. Since we were a young child, we've looked at maps, we've looked at charts. The land is always brown or green, the sea is always blue, and that's what we expect to see. By flipping those two colours, even though for people from the northeast it's a very easily recognisable coastline and most see it on the second picture, we've increased cognitive load. So something as simple as using a colour that our brain says does not fit with our preconceptions can increase cognitive load. Let's look at this chart. It's a very simple pie chart from Lewis disease, nasty, fatal disease. How have I increased cognitive load? I'll just give you a moment to look at it. Hopefully you noticed. Here we look at yellow, we're looking at the seasons here. We associate yellow with summer, but we keep having to look across here and we find it's winter. We look here, green, spring, right? Oh, no, that's fall. So I've increased cognitive load. You have to keep looking back and forth to the legend because things don't make sense. It's a minor aspect, things add up. How much better is a graph like this? Now, not only are the colours logical, but by incorporating the annotations within the diagram itself, we don't have to look back and forth. It's there in one go. It makes it a chart that's very easy to remember. Don't bother remembering it, since this is a mythical disease, however. Now let's think about how much information that we try and deliver, the quantity of content. As we increase this quantity, we decrease the learning of the really important material with it. As teachers, we all tend to do this. We want our learners to have all of the facts given to them, and we think that they will be able to fish out the important facts, and that they'll learn those, and hopefully they'll learn some of the other information. But it doesn't unfortunately work like that. And often less may actually be more in these situations. We may teach 30 facts and the students learn 5, or we may teach 10 facts and they learn 8. Which would we rather have them do? It's not what we teach, it's what they learn from it. You need to break this information up. One key learning point per slide. Have them process that information through their working memory, get it into their long-term memory before you move on to the next teaching point. We sometimes get very fixated that we must have no more than 60 slides because it's a 60-minute talk, or some kind of mythical, hypothetical number that has appeared from, I don't know where. It doesn't make any difference how many slides you have. It's how much information is on that you are trying to convey to the learners and how it is presented. So in other words, how much information is given on any one slide for them to assimilate before they move on to the next. let's look at this beautiful slide. How many learning points have we got here? Well, I don't know what any of this means, but it doesn't really matter. There's something, there's something going on here that's something important. There's this one here that involves hierarchy, a totally different teaching point. There's this one here, again, no idea what it is. There's another one or two here. There's something here. There's probably 12 different teaching points on this one slide. How can you possibly hope that some learner's going to be able to assimilate this information, learn it, and be able to apply it later? Not every word you're going to say needs to be on the slide. If you need speaker's notes, either print them out or use one of the functions within PowerPoint that allows you to be able to see your notes at the bottom of the screen, not being projected to the audience. When you put every single word you're going to say, or every single word that you want the audience to have as notes for your handouts later onto the slide, this does a couple of things. One, it tends to be an overwhelming cognitive overload, but also the audience can read faster than you can talk. So what happens then? They're reading down here and you're talking up here, so they have two types of verbal input going into their brain. The words that they're seeing and the words that they're hearing, and they're trying to process those two pieces of information which are not synchronized at the same time. Increases your cognitive load. John Sweller again, and I'll just let you read this. If every word is going to be on your slides, just send them the slides, send them a PDF of the talk, let them look at it in bed over a cup of coffee rather than having to come in and listen to your lecture. We all tend to include a lot of extraneous content both on our slides in terms of textual information and other pieces of stuff that are stuck all over the slides, but also in what we tell our learners. We go off into anecdotes. Sometimes this will help their learning process, but actually quite often it impairs them. So extraneous content is visual or verbal information which is not directly related to their learning objectives of the session. This extraneous content makes our brain do extraneous processing. It's working hard. That little RAM processor off doing the 157 different processes on the side is working and doing something with that information, even if that information is not helpful to the actual process. So when we're given a slide like this to look at, our brain is processing a lot of information here. We have a lot of numbers with a lot of decimal points, a lot of percentages all over the place. We have a little blurry ultrasound diagram down here that's too small and too out of focus to be helpful to anyone. We have a picture of, I don't know, something, but part of you is looking at it, trying to work out what that is and not listening to what the speaker's saying. We have the hospital with some icons in two different languages and so on. And in fact, I looked at this and I took out the information which really delivered to the audience, and it was this. Much easier to understand, I'm sure you agree. Even a slide like this has lots of extraneous information. We have here the 3 different diagrams. All right, do we need all of these? Do we need a picture of somebody looking at a PACS monitor? We're radiologists. We all know what looking at a PACS monitor looks like. We all know that 3 orthogonal planes are coronal, transverse, and sagittal, and so on. What could we do inside? We could just have something like this. We could just have one diagram that shows the apparatus and then explain anything else that we need to. So keep it to the facts, just the facts. Now there's a very interesting phenomenon called the modality effect that I'd like to explain to you a little bit further. It turns out that our working memory, and I'm going back here again to a computer analogy, has the ability to process information down 2 separate pathways. So it's kind of like the Intel dual processor in your laptop. It's a much more efficient way of processing information by sending it down 2 pathways. So visual information, and visual information might be a diagram, it might be a picture, it might be a graph, it might be an image or so on, goes down one pathway. And verbal information goes down a separate pathway, and verbal is both written words and words that we're hearing. So to most efficiently process information, we can send this information down both pathways at the same time. So we can send it at the same time down this, it will be very efficiently processed and get into long-term memory. But if we try and send information, all of it, in different ways down the verbal pathway, for example, that's going to impair our learning, that increases our cognitive load, and it impairs our ability to be able to acquire, process, and store the information. So, if we have an image or a scan or a picture, and we're explaining, and we are talking about it, explaining it, people are listening to it, they're going to learn it real well. If we have our picture and we have some text with it, so for example that might be text on the side of an image, or it might be an image that's in a book with some written explanation and so on, we do okay. Not quite as good as we did with the spoken. Good. If, however, we have text and then we're talking about that same text, people are listening and reading the words at the same time, this actually impairs learning. They won't learn as much as they did in the previous two occasions. So it turns out that the way that a lot of us lecture, lots of words in the slides and then talking about them, is really not a good way of teaching whatsoever. Here's an experiment that showed the modality effect quite nicely. So this was a diagram that was shown to a bunch of college students. It was a chemistry diagram explaining how a material or compound goes from solid to plastic to liquid and so on. 3 different groups had this diagram explained to them using 3 different methods. Now here's that learning efficiency diagram again, just to remind you how well they learned it is on the y-axis, and how hard it was to learn, the mental effort, is on the x-axis. So when they took this diagram and they used an audio explanation, it was highly efficient learning, students learnt really well. When they used text to explain it, not quite as good. When they used audio and text, so they were kind of using the belt and suspenders approach here, it actually impaired learning. Split attention is another interesting phenomenon that often affects how much our learners understand and remember from any of our teaching. I think those of us who have teenage daughters or sons are pretty aware of this type of extreme split attention, but I'm talking about something much more subtle. By doing something as minor as separating in space, text and graphics, we split a learner's attention. They have to look at the images, they have to look at the text. For example, when you're reading a textbook and it says see figure 4.A and you flick through the pages and find 4.A, then you look back to the text, read a bit more, then it says look at figure 4.B and you go to a different page to find 4.B. That splitting of attention impairs learning by producing a high cognitive load. If any of you have ever used a manual to be able to learn how to use a software program on a computer, this is a sort of extreme example of it, and I think you know how difficult that is, compared to the sort of teaching programs where everything is integrated onto the screen and you're hovering over something to learn a new function and so on. Even taking notes can be a very high cognitive load. And in fact, they've shown that note-taking during a lecture can be as high a cognitive load as playing chess. The learner has to listen to the lecture, they've got to look at the slides, they're trying to work out what's the important information, they're trying to get that important information down, either writing or typing, and then by that point they've moved on a slide or the lecture's talking about something else, so they're trying to listen to one thing while write down the previous thing. It's an extremely high cognitive load. Again, increasing cognitive load impairs your learning. Here's part of a study, I'm going to show you the second half later in this talk, which showed this. So these learners were given a lecture. One bunch took notes, the other bunch didn't take notes, and interesting enough, the students who did take the notes scored worse in the exam that was given at the end than those who did not. So, for example, this would be a common slide I might show medical students if I was giving a talk about subdural and epidural hematomas. So I'm going to give them this text slide here, talk about it a bit, and then I'm going to show them an image of a patient who has both a subdural and an epidural hematoma. And while I'm talking about that and I'm waving my laser pointer around, they're trying to remember what was on the text slide before that I'm now demonstrating. I've split their attention. Now I could reduce this by putting all the information on one slide. The image gets a little bit small and they have to look from left to right, but at least they can link the two much more efficiently. Or even better, I can incorporate the annotations into the image itself like this, so they don't have to try and link the two. I'm already doing it for them. Or a final way, which I'm actually most likely to use, is I'm going to show an image and then I'm going to do active annotations, talk about how the mass effect is shown, then I'm going to talk about the characteristics of the epidural hematoma, then I'm going to, I might erase all these, and I'm going to move on and I'm going to talk about subdural hematomas more efficiently like this, and so on. There is no split attention involved with this. They're engaged, they're watching it, it's easier to follow than a laser pointer, and I highly recommend it. You can do this easily through PowerPoint with a mouse if you're fairly have a good mouse, or you can use a tablet or an iPad at the moment. Use images in your talks. I'm a radiologist. We obviously use lots of images because a radiology talk with no images is a pretty bad talk. But as well as scans, by using images that provide some form of an emotional connection, this will increase their learning. It's kind of like there's something to hang the memory on there. But clip art doesn't really work. Clip art, there's no emotive response to it. If you were trying to do a talk on childbirth, for example, which one is going to provide that emotional connection to when you're talking about the pain of childbirth, the image on the left or the image on the right? Interesting enough, if you have self-explanatory visuals, be they graphs or diagrams, and then you add words to them, it can actually suppress learning. One study looked at two groups of subjects who had never flown before. No idea where they found these candidates, but anyway, they showed them this diagram that you're probably very familiar with, showing them how to do up their seatbelt and what to do in an emergency and so on. One group of subjects had the text attached to it, and one group of subjects, these were given to them without text. The subjects were then tested as to what they learned from it. And interestingly, the group of subjects who were not given the text explanations could understand these diagrams better. So adding the text suppressed their learning because they were self-evident. So we've talked about how much information you try to deliver to your learners. We've talked about how you might deliver that information. And now let's think about who you're delivering it to. People talk a lot about being visual learners or verbal learners. Pretty much every med student who interviews a radiology residency tells us that they are definitely a visual learner. This isn't really helpful, but mostly because all of us learn both visually and verbally, even if we have a slight preference one to the other. But also our audience is always going to be composed of groups of people who maybe some of them learn better visually, some of them maybe learn better verbally. They all can learn both ways, but you don't know who's who. And unless you really want to give two lectures, one biased to the visual learners and one biased to the verbal learners, who can all turn up at different times and self-allocate themselves into those groups, then this is not going to be a way that you're going to change your teaching. There is, however, a much more important distinction, and that is whether they are novices or they are experts in a particular subject that you are teaching. Novices and experts learn very differently. There was a very interesting experiment done that took two groups of subjects. One were chess masters, the other group of subjects had never played chess. They took these two groups of subjects and a chessboard, they played a chess game halfway through, and then they asked each of these groups to memorize the positions of the pieces. Not surprisingly, the chess masters could remember many more piece positions correctly than the chess novices. In the second experiment, took the same board, the same number of pieces, and this time they placed them randomly on squares of the board. Again, asked the two groups to be able to memorize them. And in this occasion, the chess masters performed significantly worse than the chess novices. And the reason was that the chess masters, they weren't merely memorizing the positions of the pieces as the novices did in the same study, and the novices, by the way, scored the same in both experiments as you might expect. But the chess masters were using their long-term memory in these very complex schema that they've developed over the thousands and thousands of games of chess that they had played, that the pieces in the first experiment made sense. So they memorize the pieces by kind of playing the game through in their mind, on a subconscious level. In the second experiment, the pieces did not make sense. They couldn't use that, so they were having to resort to be able to learning them merely by rote at the same time. It wasn't making sense, and it increased their cognitive load, and they learned less. Here's another experiment that showed similar results. In this experiment, they took a group of engineering students and they were teaching them about drilling speeds. They had a diagram that had a couple of different explanations, both a diagram with an audio explanation and a diagram alone. Their two groups of subjects were students in the first year and students in the third year, with the third year students being the, quote, experts. So in this experiment, when they took the novices had much more efficient learning when there was an audio explanation with the diagram than when they were just trying to figure it out by themselves. But in some way, for the experts, they did better just with the diagram only, and the audio explanation impaired their learning. They'd got some kind of pre-existing complex memory schema that having that audio explanation affected their learning in some way. So one size does not fit all. You can't teach the same material to a group of novices in the same way as you would to a group of experts. Note that the term novice and expert is not dependent on the age or of the learner, but their experience within that particular subject. So I might learn as an expert in breast imaging, but if you put me into a mechanical engineering class, I'm going to be learning like a novice. So for novices, cognitive overload is extremely common, and it's really important for them to have some kind of a foundation framework, and this might be provided in some form of pre-learning before your lecture, for example, for them to be able to add this additional information to. So if you're teaching to a mixed group of learners, for example, first through fourth year residents, your first years are novices and your fourth years are much closer to the expert level, you may need to provide those first years with something to look at, maybe ask them to read a chapter, ask them to look at a short video that you've recorded before they come to the lecture to be able to get the most out of it. Otherwise, you're always going to have to keep it down to the novice level, which is not going to be great for the more senior residents or students, or you're going to risk having cognitive overload for those novices. Novices have to have a much more staged approach to their learning. If you take a bunch of people who are experts, they have pre-existing long-term memory patterns. They're able to assimilate information faster, much more complex information, and that information being delivered in a more complicated way. I learn medicine now in a very different way than I did when I was a medical student. However, as I said, if I was going to be learning a totally new subject, I would be back to being a novice learner, and I need to use novice learner methods. One of the challenges often is that we often have an audience with mixed members. So we may have students, we may have residents, we may have our colleagues, we may even have some people who are not formally medically trained at all, and it can be quite a significant challenge to be able to make our teaching approachable and understandable for all of these different groups. In this second section of this lecture, I'm going to try and demonstrate how you may be able to make your lectures much more brain-friendly to your learners using some of the cognitive concepts that we've been discussing. First of all, simplify all of your fonts, your colors, and your backgrounds. I know it's boring, but take out all those icons of fancy schmancy backgrounds with seashores and everything going on. Just take it all out. Just a plain dark background or white, which I'll talk about a little bit more in Really, the key to this is that the more readable it is, the easier it is for people to learn the information. So, for example, even something as simple as having a font, which is a sans serif font, sans serif, is written like that. In other words, it's the fonts that don't have the little tails on the letters, such as that Times Roman does. So a font such as Arial, for example, or Helvetica has been shown to be much easier to read when it's projected on a slide as opposed to being in a book. So a slide like this, which has, I don't know how many different fonts, a bunch of different fonts here, and many different colours, and little jumpy creatures here. You know, if I wasn't already an atheist, this would definitely convert me to atheism. Fancy fonts don't improve learning. They just add to the cognitive load. Having all your slides in capitals means that it's interpreted as shouting by your brain in a similar way to if you get an email where it's all written in capitals. It's like somebody's yelling at you. An entire lecture in capitals, you're being yelled at for an hour. The colours need to be clear, and they need to be clear not just on your computer monitor, they need to be clear when they're projected in the auditorium. Animations can be particularly distracting unless there's a really good reason to animate that text or animate that picture, then take the animations out. The same with slide transitions. Just appear or disappear. Don't do fancy transitions, and for God's sake, keep the noises out of there. Here's an image one of my colleagues took at the RSNA. Red on black, not good image contrast. Standardize the fonts and the layouts of your slides such that each sequential slide has the same fonts with the information presented in the same way. By doing this, people can find the information they're looking for much faster. Just make areas you want to emphasize bold or italic, or perhaps add one additional color. Think about how it reads from the back of the room. At the bottom there's a line in 24 font. Now this looks just fine on your computer screen, but it's not necessarily going to look when you're in the back of a lecture hall. And where do our students and residents sit? In the back. This is a slide that's in 24 font from the second row of a lecture theatre. Very difficult to read. In comparison, this, although it is capitalized, and we've already talked about that, is in a much larger font. This is probably a 44, 48 font, very readable from the back of a very large lecture hall. Most of my slides, I use a minimum of 40 font. Think how it's going to project in the room that you're going to use, whether you have a light background or a dark background, whether you're including radiographic images in your talk or not. In a bright room, this looks great. In a dark room, this looks better. Be kind to their eyes. A very bright background in a dark room makes your pupils constrict. If you're going from a light background to a dark, to a light, to a dark, people's pupils are dilating and constricting. This causes eye strain when you've been doing it for an hour. If you have images, they're going to show much better if they're on a dark background than a light background like this. Much easier to look at, your pupils will dilate and be able to take in much more subtle details. Put every image and every graph on a separate slide in your presentation. Just because PowerPoint gives us the ability to be able to put 100 graphs on one slide, it doesn't mean that we have. There are some data tables. Some tables contain so much information they should never be shown as slides unless they can be broken up into very small components. Keep your graphs clear, large, one slide, one graph. Same with images. Unless there's a reason to put more than one image on a slide, put one up, describe it, explain it, go through it, and move on to the next, and particularly for our more novice learners. So a slide like this, and you're talking about something up here, but they're looking down here, they're wondering what this blue and red stuff is here. Just one image on, talk your way through it. Notice I've also incorporated my annotations into the image here before you move on to the next. For a presentation, not a paper, summarize your tables. You can't go through every line on a table during a talk, so summarize it. So even a table like this, which is not a very complicated table, and we've all seen many words during presentations, but there's quite a lot of data on here, and which bit are we supposed to be reading and focusing on it? It's one slide of a series of slides in a 7-minute talk, so not that much time can be spent on it. Summarized down to something like this. Much more readable. We know immediately that we have to go across to look at these red and highlighted areas over here, and these are the ones that we're going to focus on. Reduce the amount of text you have overall through the talk, and particularly how much is on any one slide. If you need to include the text, then break it up over a series of slides rather than one. So a slide like this contains much more information in much too small a font to be able to adequately be covered, let alone learned, during a presentation. So pull out the most important stuff. In this case, it was this that you really want to be able to focus on during your presentation. As I said before, you want one learning point per slide. So let's go back to the slide I had talking about subdural and epidural hematomas. How can we better present this information? Well, we could do it like this. I might first of all just take mass effect, talk about how extraaxial blood, in this case a chronic subdural, has mass effect, and explain that until I was sure my students understood it. Then I would move on and talk about how the density of blood changes with time within the brain, and this one happens to have both hyperdense, isodense, and hypodense components, and I can talk through that. Move on and talk about subdural hematomas and talk about how they looked and all these different features and explain them one by one. Then finally I would talk about epidural hematomas and talk about the imaging features of those and work my way through this one image. By doing this, we're doing called chunking information together. When we memorize stuff, we chunk it together because that helps us both with learn it, and it particularly helps with recall of information from our long-term memory. And I have kind of pre-chunked it for them. I've put the groups of information together in a way that it's much more learnable for the medical student. Take out every abbreviation or acronym that you possibly can. It's very irritating to be attending a lecture and some acronyms come up and you have no idea what they stand for, because the lecturers assume that everyone in the audience will be familiar with them, and often they're not. And your learners often don't want to have to put up their hand and say, excuse me, what does PIH stand for in this particular situation? You know, hopefully, this of course is a slide from the government, in case you hadn't guessed. We don't produce slides that are quite as bad as this. But most lectures have some mystery acronyms and abbreviations scattered throughout them. When you're giving your presentation, signal the key information within it. This can be done both verbally, when you're presenting the talk, and visually on the slide itself. This is going to help the learners retain information, and it also decreases their cognitive load, particularly when they're trying to take notes. I'm going to show you half of that experiment which I showed you earlier. So if you remember, this was the experiment where the students who took notes scored much worse in the exam than the students who didn't. This was in an unsignaled lecture, so this was the lecture just being given like most of us give. If in the second experiment the lecture was signaled, in other words, the lecturer focused the students' attention on the pieces of information they really needed to know, both verbally and visually. Verbally you can do it by, and the most important thing to remember, a key point here, it's really important, a major determinant of, and so on. These are called signaling clues, or we can do it visually on a slide by highlighting or bolding and so on. And in this second experiment, as you can see, the students who took notes did, as one might anticipate, better than those who did not, because the cognitive challenge which was associated previously with them trying to filter the information and work out what they need to write down and what they didn't was not there. Sometimes it can be something as subtle as just highlighting the value that you're going to really focus on a table, or highlighting the most common causes of a finding or an abnormality within a longer list of them. Think about replacing some of your text with images, particularly those that are going to create some kind of an emotional connection with the material about to present. It also becomes a good way of separating and linking different topics within your. Remember that modality effect we talked about before. If you have an image, try and use an auditory explanation of it rather than using a textual explanation, or worse, both. Do we really need text to be able to explain the occasionally fatal consequences of a ruptured ectopic pregnancy? And finally, always practice your talks verbally. I often end up changing a lot of my slides, both in terms of their content and how they're laid out, once I practiced it verbally for the first time and realized that it's not going to be very understandable to my learners if I keep it as is. Quite aside from anything else, particularly if you have a talk that is a very short talk, such as a presentation at a national meeting, until you've done it verbally, you really have no idea how long it's going to take. So practice to the dog, practice to your kids, or talk to a chair. It doesn't really matter, but you need to say those words out loud. So in summary, by reducing the cognitive load that we present to our learners, we will improve their learning. And we can reduce the cognitive load by considering the audience. Are they novices? Are they experts? Are they a mixture of both? And if they are, you may need to do some form of pre-learning for the novices. By limiting how much you're trying to teach them in any one session. By simplifying your presentation style as much as possible, keeping those slides very simple, no extraneous information, only one learning point per slide, and so on. Remember that modality effect. So don't put up lots and lots of text slides and then be talking about them. Try and use images some more. Reduce their split attention by incorporating annotations into images, by signaling your lectures as much as possible, by providing them with decent handouts so they don't feel that they have to take notes. Here's something I saw that is something to think about, the 40-10 rule, that the first 10 slides should have no more than 40 words in total on them. Use these first 10 slides as your opportunity to be able to capture the attention of your audience. Use images. Build the story around them that you're about to tell. So in this last little piece of the talk, I'm going to show you a series of slides. I'm going to keep quiet for a few minutes while you look at them and have a think about what you perceive as to be some of the problems on the slide, and then I will point out some of the issues. Here's the first one. I'm going to give you about 15 seconds to look at it. So let's think what we have here. Well, poor contrast up here, lots of different colours, unnecessary stripes and bands. You know, do we really need to have pictures of flowers down here? Another one here that you have to kind of squint at and try and work out if what that is. Is it to do with the talk or not? Which it clearly isn't. A couple of different types of bullets. Then an eye is drawn to these letters that are in italic and red. Makes us think that those are the most important thing to learn on this slide, but when we look at it, we just have micro-calcifications, but not all. So that actually makes no sense. What else? This is very small font. It's not going to be very readable from the back of the room. Let's have a look at the next slide. Again, I'll give you a few seconds to look at this. So what do we have going on here? Well, we have some very, very small font up here. We have a graph, this is not going to be readable, and a table and text all on the same slide. So wouldn't this be an awful lot better being separated out onto separate slides where you can then individually go through them? We have a lot of abbreviations. Maybe they were explained in an earlier talk, or maybe they weren't. Let's look at this table underneath. You know, we have 3 decimal point figures being given. Do we think that the study was accurate to 3 decimal points, or this test is accurate to 3 decimal points? That's really pretty unlikely. So there's an unnecessary number of figures here on the table, and this table could be definitely simplified and put on a table by itself. How about this one? Well, what do we have here? Oh, we're back to more abbreviations, of course. This is bolded as being the most important information on here, but I'm not sure what it is. There's kind of an interesting bullet step off here, which my eye's drawn to, but you don't know if it's a mistake or it's actually supposed to be inset. Then there's this diagram / figure here, which is small, unreadable, and likely completely unhelpful. We really don't, for the purposes of a scientific presentation, need to see the table which people are using to input their information. It just cramps up everything else. And now this one. So our eye is drawn to this green box because it's a different colour than the rest. Is that the most important information on the slide? I'm not sure that that is. How's the information on that, the level of importance of that compared to the purple and red, or the red box here as opposed to the green and grey boxes back here? Perhaps a lot of this text that we see here and here and here could be put on a preceding slide rather than trying to put it all on the slide with the actual flow diagram. We have at least 3 different fonts here to add to the challenge. Here's another one. What do we do first of all? Well, this graph would get blown up and put on a separate slide, not put on the same slide here. These are not very clearly distinguishable colours. It's very difficult to read this graph and work out what is a fibroadenoma. I do actually know these abbreviations. What's DCIS and what's an invasive ductal carcinoma? Hopefully those abbreviations were explained elsewhere, or at least verbally, by the speaker. As I said before, there are some tables which should just never be displayed in a talk. If the key information of this cannot be consolidated onto a slide, then this should be completely omitted from the presentation. I'm going to show you 2 slides that came one after the other in this same talk, and see if you can see what the issue that's causing an increased cognitive load is. So this slide here, which you've seen before, and then this slide here. So neither of them are terrible tables. This one's a little better than the other one. But what's the increase in cognitive load? Well, on this one, A, B, and C are row headers. On the prior slide, they were column headers. Why not keep them the same to make it much easier for people to follow from one table to another? So that's all I've got to say in this lecture. I hope this has given you some guidance and will help you improve your talks and make them more brain-friendly to your learners. Here are some additional resources which are worth looking at. Many of the studies that I reported came from this book here. This is a very readable book and well worth having a look at if you're interested in this subject. Thank you very much.